I'm going to talk to you today about depot autonomy. And, one of the things I always like to do is, I just love generative AI, right? So basically just like write a prompt, which is down in that corner, sort of describe what I'm doing, put it in and see what AI thinks of what I'm doing, right? Like, so how would AI imagine depot autonomy, basically, right? So, generate a colorful, detailed illustration of a spacious interior of a fulfillment warehouse, with modern delivery vans being marshaled around the infrastructure autonomously, and this is what AI thinks is, which I thought was really cool, actually. Dolly's my favorite. It's really nice, sort of futuristic looking renderings. So, we'll talk a lot about depot autonomy today, but we're going to start really broad and then sort of, narrow in as we go on depot autonomy. But, first off, wanted to give you all an idea of who I am and what my background is. So I've been at Mcity for 2 years now as the research director. But prior to that, I spent 34 years at Ford Motor Company, where I was the chief engineer of the driver assistance features. So, if you've driven Ford vehicles, pretty much any of the driver assist features you interact with are ones that came out of originally my team. Blue Cruise is probably the one that we made that's the best seller, sort of driving with your hands off the steering wheel, your feet off the pedals. It keeps you centered in the lane and space from the traffic ahead. You do need to keep your eyes on the road. It is a level 2 SA level 2 feature. We also did all the collision avoidance features, automatic emergency braking up through all the intersection assist features, and then all the parking and trailering features as well. So it was a really nice experience for me. Great group of people to work with, learned a ton. And now it's time for something new, right? Which is come to academia and spend some time, looking at the state of the art and how can we move that forward. And so specifically, what sort of industry shaped research agenda, do I want to focus on at Mcity was really sort of, as research director, that was sort of the first task I needed to figure out. And the 3 topics there, I'll go in more depth on the next slide into them, but those are the principal ones I'm working in now with our team. In terms of my background, university-wise, my undergrad was at Princeton University, and I got my master's degree at Stanford. And I have 6 kids, 5 Wolverines. One is a senior who just graduated a couple weeks ago, and I've got 2 who just completed freshman year. And then 2 who've graduated and moved to Manhattan, and our Indiana Hoosier is in Chicago now. My Wolverines is my big connection to U of M. Thank God for in-state tuition, right? But otherwise, I'd be working infinitely, I think. All right, the research agenda. So this was sort of the idea of me coming into Mcity as the research director, was to say, I've done this, 34 years of industry experience at Ford. What are some of the important trends that are sort of emerging that we could shape a research agenda around at Mcity that would be relevant for industry? And so it's really the 3 there in the colored boxes. The top one is this idea of, digital and physical reality sort of converging right now, right? So at Mcity, we've created very realistic digital twins, which we've made open source available. And, the quality of those digital twins is really converging with reality to the point where at sometimes people have to ask, like, is that the digital twin or is that a photograph, especially as we get into things like a Gaussian splatting digital twin that we're working on. And then that's the idea of the converging. The synchronizing is the idea of making it so that, for instance, when the traffic signals change from red to green on the proving ground, having them also change red to green, that particular signal in the digital twin, right? So keeping the physical and the digital world synchronized. And then mixing is this mixed reality idea where we can take a test vehicle and we can drive it on the track. It has sensors, and so it can see all the things that are physically on the track, but we can also drive it in the digital world simultaneously. So we can also make it see a whole bunch of stuff that's in the digital world that's not in the physical world. And that ends up being a good way for us to do things like risky scenarios where maybe a pedestrian is jaywalking, right? You'd rather do that with a virtual pedestrian when you're testing an AV rather than a real pedestrian. So that's a lot of the work that we're doing there in sort of bringing together digital and physical realities. Artificial intelligence, I think, is just tremendously important. It's reshaping our lives. But a lot of, what people are doing is sort of artificial intelligence that lives in data centers and predicts next words and things like that. And so the cost of hallucinations there is maybe not quite, critical. It's annoying, certainly. But once you start putting artificial intelligence in safety critical applications, then it becomes very important to make sure that what artificial intelligence is doing is correct, right? Because if you think of artificial intelligence controlling a self-driving vehicle, right? Or, a drone or a mobile robot or something like that, right? The consequences of the AI hallucinating and doing something strange could be safety critical, right? People could get injured. So this idea of not just how do we advance artificial intelligence, but how do we do it in safety critical applications where, the hazards are really, really important for us to assess and mitigate. And the two projects we're working on there are an AI data engine, which allows us to take some data, fit a model to it, test it, deploy it into the real world, see where it works or where it doesn't work. For the places it doesn't work, gather up new data, add that to our data set, retrain, retest, redeploy. So that's the data engine we're creating, and we're in the process of making it agentic so that we'll have natural language interfaces. So you can talk to the data engine. Abe is our engineer doing the data work. And so he's sort of creating an Abe agent, think of it, right? Like if I say, Abe, I want you to do this, right? That's what I do today. In the future, I can talk to the Abe agent and give the same sort of interaction, right? So this whole idea of agentic interfaces, I think, is really important. The other important one we're working on there is an AV safety assessment. So right now, companies release AVs into the world when they believe, they're good enough, and when the local permitting authority will issue a permit. As we've seen, when accidents happen, like Cruz's accident, society sort of looks at that and goes, hey, wait, nobody asked us. Right? You're driving around our streets, but you didn't ask us whether we thought that was okay, right? And so it's sort of galvanizing this idea of maybe there needs to be third-party assessments, right? And maybe there needs to be a larger societal discussion around how good is good enough. And so we want to be an important part of that discussion. And then the third one is this idea of infrastructure-assisted autonomy. So right now, if you think about AVs, right? AVs are autonomously autonomous, right? They do everything on board. They have all the sensing on board. They have their maps on board. So everything happens on the AV. But, it's ignoring the fact that there's a lot of sensors going into the world, right? We have sensors. If you drive around Ann Arbor and look at any intersection, you see a whole bunch of sensors at all the intersections, which at Mcity we're tapped into and get data feeds from. Likewise, sensors are being installed along highways. There's a lot of infrastructure that's going in that's connected to compute that can make useful information that the AVs could benefit from. So given that this is happening anyway, that the infrastructure is getting more instrumented and smarter, how can we help AVs safely deploy by giving them access to that? And the specific use case that we're going to spend the rest of the time talking about is our depot autonomy project. And so let's first talk about autonomous vehicles. So vehicles that are not communicating with each other or communicating with the infrastructure, right? So this is, created a news story because these Waymo vehicles at 4 a.m. were trying to park themselves in a parking lot autonomously. And they're all getting in each other's way, right? Because they all have their own individual AV stack that's individually trying to make a decision. And unfortunately, they're also programmed to honk when somebody's blocking them. So it's 4 a.m., they're all fighting with each other, the parking lot is gridlocked, and they're all honking at each other. So, clearly a failure mode. If you think about this, right, you've got lots of places you could mount cameras around this parking lot. You've got light poles there that have electricity. You could put cameras on there. With just a small amount of instrumentation and some compute, you could have something that says, hey, this vehicle should park in that space, and this vehicle should park in that space, and this vehicle should park in that space, right? And they could all be sort of centrally coordinated, and the gridlock would go away, right? But that's not happening because all of these vehicles are sort of individually autonomous and not having any sort of central control. So the idea is with infrastructure instrumentation already happening, right? Because people are putting cameras on light poles for security reasons, right? Not even for autonomy use cases, right? So the sensors are out there. You just got to connect it up with a little bit of compute, and you could have central control that would help alleviate situations like this. So, that's basically the general thesis of infrastructure assisted autonomy, is that it's happening anyway. How can we use the infrastructure investment that's happening to accelerate safe and efficient autonomy? Then we get to the question of, why did I pick depot autonomy? And the reason for that we'll go through in the next bunch of slides, but it's basically that within the automated driving space, people have really sort of found out very efficient ways to lose large amounts of money, but nobody's found a really efficient way to make a lot of money. And so that's been one of the curses. We'll talk about the curses on the next slide, but really one of the things I want to address is trying to find a use case for autonomy that clearly can have a profitable business case. Cruise, I think GM said something like Cruise spent like $15 billion or something before GM shut it down, right? It's a lot of money. Waymo's been doing it for 15 years or something. I would imagine they probably spent like $100 billion now. There's no way they're recouping that investment. They're doing it because it's cool, and God bless them, because it really is cool, and it's going to be important for safety. And so I love the fact that they're doing it. But, they're doing it because they're rich. They're doing it because they got a search engine, which is throwing out ad revenue like crazy, right? And a lot of us don't have that, right? So we need to search for things that have better business cases. And so depot autonomy, the core idea of depot autonomy is we've got these Amazon packaged fulfillment centers where, drivers drive vans in, they drive it to get loaded, they drive it to get washed, inspected, you know, they maybe have to get recharged. But you got a driver who's marshaling the vehicle around that yard or the depot of the fulfillment center with a small amount of, you know, coordination of security cameras in that warehouse. Could we actually take those level 2 vehicles that just have the normal cameras and radars that like a Ford Blue Cruise vehicle has? Could we take that onboard sensing that's already on the vehicle and the sensing in the infrastructure that's already there for security reasons? Could we combine those two things with a little bit of compute and smarts and make, you know, those level 2 vehicles able to operate, you know, as level 4 autonomous vehicles? So that's the basic idea. So, you know, this is I always like to start with the really simplified sort of toy version of the problem, right? To just sort of make it clear, you know, what we're talking about is, say you've got, you know, a warehouse here and it's inside a fence line, which is really nice because if it's inside a fence, that means you don't have to worry about the general public, right? So there's nobody who's, you know, drinking too much and jaywalking. You know, everybody's an employee. They've all been trained. We can put safety vests on all of them so that they're conspicuous, right? So being inside a fence line actually really, you know, creates a real sort of reduction in dimensionality of the problem. And then you would have your drivers come in. They would drop off the van in the, you know, the lot for empty vans. They would go pick up a loaded van and then they'd go out and deliver packages, right? So you keep those drivers on the road delivering packages, right? Because that's the real revenue, is getting packages delivered quickly. And then this vehicle then with the help of the infrastructure sensing would be autonomously moved, you know, to get loaded, to get charged, you know, to get cleaned, to get inspected or repaired. You know, because you want to make sure you catch any problems on the vehicle when it's in the yard, not when it's out on the road delivering packages, right? So that's the sort of very simplified view of the depot autonomy challenge that we're working on. So then let's talk about these things that have limited AV deployments, specifically in the context of depot autonomy, and how am I addressing these different pursuits of autonomy. So yeah, like I said, you know, Waymo, I mean, they started, everybody became aware of what Google was doing when they started driving the Toyota Priuses on the road in 2009, right? So a long time ago. That was, you know, and I'm sure they had started a couple years ahead of that, you know, because they recruited a lot of people who came out of the work in DARPA Grand Challenges. So people have been working on this space, you know, for a long time. And people have been thinking about it since the 1950s, you know, so it's been an idea out there that just has failed to launch, right? And it's starting to launch now, because we're chipping away at these curses. But the first one, the curse of dimensionality, is just this idea that when you put an AV out into the unconstrained world like downtown San Francisco, there are just so many variables you have to deal with, right? And so very quickly, the dimensionality of your problem becomes just completely exponential. And so back in the day when we were creating the original sort of AVs, we were sort of hand coding algorithms to you know, do the autonomous driving. And what we quickly found is that as humans, we are not good at crafting algorithms for very high dimensional problems, right? We can handle a couple dimensions, but when it becomes really high dimensional, it's beyond us. But then AI has come onto the scene. And so sort of in about 2015 is when you saw a lot of the AV companies really make a very determined paradigm shift away from sort of the hand-coded algorithms into the AI algorithms, because that's the great thing about AI, is right. You give it these, this really rich data set with all the dimensionality in it, and AI finds the hidden patterns in that embedding space that are very hard for us as humans to find. So that's the real progress we've made on the curse of dimensionality. The next one is the curse of rarity. So once you've made an autonomous vehicle that drives really well 95% of the time, then you get into the last 5%, right? And it turns out that the first 95% is dramatically easier than the last 5%. Because the last 5% are those really rare cases, like the accident that the Cruise had that ended up, effectively in GM to pull out of their investment there. That was a situation where, pedestrian was crossing in a crosswalk when they shouldn't have been. A human driver hit the pedestrian, threw it in the path of the AV. The AV drove over the pedestrian, and then, the real thing that made people mad was, instead of the AV just staying there, it decided that it should get out of the way of traffic, and so it tried to move off to the side of the road, and it dragged the pedestrian under the vehicle. So yeah, tremendously rare situation, right? If you're thinking about an engineer sitting down doing a hazard analysis, right? That's not a hazard you would have imagined, but it happened. It really happened in the real world, right? And so that's the difficulty of the curse of rarity, is it's very easy to find data of normal driving and to train a really great AI model for normal driving. But if you want to capture 1 in a million events, then you've got to drive 1 million miles to capture one of those events. And driving 1 million miles is very, very expensive if you do it physically. At Mcity, we're trying to attack the curse of rarity by doing a lot of work in simulation. But then, of course, you have to address all the scenario gaps, because right now, the gold standard is the real world driving, and simulation, we have to prove that it's as good as real world. So limiting dimensionality, limiting the occurrence of rare events are two things that why I'm focused on depot autonomy, and I'll take it through specifically why. But then the third one is the curse of unprofitability, right? So yeah, most companies can't afford to just burn piles of cash, right? You've got to have a profitable business case. And I'll take you through, the business case work that I've been doing together with a team from the Ross Business School. And we'll talk through profitability as well. So this is sort of the elevator pitch for depot autonomy. Because anybody pitch an idea should be able to pitch it in an elevator ride. Unfortunately, my elevator pitch goes over 2 slides in PowerPoint, which means only in very tall buildings with very slow elevators will I ever be able to make this pitch. Basically, there's sort of 4 main points. The first one there is the total addressable market for package delivery and warehouse work is expanding like crazy. Warehouses are being built everywhere. People are expecting that I can go into Amazon, this morning at breakfast and order something, and it'll be there by the time I get home, right? And so it's just a tremendously growing market. And the thing that's holding this market back are humans, because these warehouse jobs are not good jobs. They are very strenuous. People get hurt a lot. They don't pay very well. So, we heard, our Ross team did some research and found out that like the average tenure for a warehouse worker is something like 90 days. So there's just tremendous turnover because people go and do these jobs and they get hurt, or they, figure out that I'm working too hard for this. But it's great work for Autonomy, right? And so this is a tremendous use case. And because of that, there's a lot of investment interest. I think we're going to see warehouse automation just absolutely take off. And so the market is growing. That's the first point. The second point is I see a way that we can make money by limiting our costs, right? And the way we limit our costs is by reusing existing systems, right? So if you think of the Amazon Rivian vans, right? They already have cameras on them. They have radars on them. They have compute on board, right? So I can reuse what the vehicle already has on board and supplement it with cameras, that are in the infrastructure like security cameras, and then a central sort of control room in the warehouse, which most of these warehouses have a central sort of logistics control room anyway, right? So I can reuse stuff that's already paid for other reasons, which means I don't have to bear that cost on my business case. And then I can get, increased throughput, increased efficiency. Some people that we've talked to have said that just moderating the injury rate of humans would make this profitable, right? Because once you start injuring humans, your costs go up significantly, not to mention the fact that you dramatically impact some people's lives negatively, right? So the Ross team that I'm working with is feeling like we've got a good shot at a positive business case, which, like I said, given the curse of unprofitability, is actually fairly sweet. I still don't personally understand how robotaxis will be profitable, right? You take a $50,000 vehicle, put enough instrumentation and compute on it to make it a $200,000 vehicle, and you're replacing a relatively lowly paid Uber driver. So that's your cost savings is, you don't have to pay the Uber driver anymore, but you got all that investment costs in the vehicle. You got to build some sort of a depot similar to this for the vehicles to get serviced. Maintenance of these vehicles, given how high tech they are, is going to be really expensive. So I've yet to see, sort of a robotaxi business case that makes sense to me. Like I said, there's a lot of bad business cases out there. I think we have one here that's got a shot at being good. Then the next 2 points, the way we were dealing with the curse of rarity is by keeping our scope technologically feasible. So we're not really trying to boil the ocean like bounce around San Francisco, which is really, really hard because, you have humans doing a lot of really things that you have to deal with, right? We have, fence line around our depot. Everybody's, a trained employee. We don't have weather concerns for the indoor driving. Be good lighting so we can see everything. If accidents do happen, they're going to be low speed accidents, right? Because we're only moving maybe 10 miles an hour. So your risk of majorly hurting people is significantly less when you move slowly. Plus, if you move slowly, people can react, more reaction time. So keeping our operational design domain small and well-defined really helps us both with the curse of dimensionality and the curse of rarity. And then the other thing, in any pitch, is why is what we're doing unique, right? Why can't just anybody do this, right? And the thing that we're going after, and I'll talk about it, is this idea of a type 3 system, which is a combined system where the vehicle and the infrastructure are working together. Everything else on the market to address this use case is either type 1, which is vehicle centric. That's sort of like the Waymo approach, where you put everything on the vehicle, nothing in the infrastructure. or they're doing the type 2 approach, which is you put everything in the infrastructure and the vehicle is just effectively, a robotic slave to the infrastructure. It just goes exactly where the infrastructure says it should go. And the reason people are taking those two approaches is because if accidents occur, whoever's making the system is responsible for those accidents, right? And so they want to control everything, right? One company wants to control everything. So either Waymo wants to completely control the vehicle, or like in these type 2 systems, like Bosch put a system in the Stuttgart airport with Mercedes, but sort of Bosch owns the whole system, right? Type 3 is hard because now you've got these safety critical hazards and you've got two different companies, an infrastructure company and a vehicle company, having to work together to ensure safety. And so that's harder, but it's more optimal. And I'll tell you about that in a slide coming up in terms of why the partitioning of the work is more optimal. So it's more optimal systems engineering. So that's why I want to take on that, because I think that just requires some good work. That's what we're all good at. And we do have a systems engineering team on that. Maybe check here. For the Depot Autonomy Systems Engineering team, do we have anybody in the room? Maybe all online. But we do have a team working on that through spring and summer term. So let's talk about partitioning of the work and why this type 3 is the most optimal partitioning. The basic idea is that we're partitioning the work to whichever thing can do the work best. So if the infrastructure is best suited to do the work, we should partition the work to the infrastructure. If the vehicle's best, we should partition it to the vehicle. You see in type 1, irrespective, everything's the vehicle's responsibility, and in type 2, everything's the infrastructure's responsibility. Here we go through and we think about all the different tasks, and we decide where to partition them based on who's best. Like provisioning a map or a world model of the depot. Like the infrastructure knows that. It has the sensors, it's monitoring the world model. It knows what the whole world of the depot looks like much better than one individual vehicle knows what that world looks like, right? So that's a clear example of a task that's better done by the infrastructure. But if you go down to the ones at the bottom, if you think about like, a person jumps out from behind an area of shelves right into the path of the vehicle, right? The vehicle's going to see him instantly. I want the vehicle to be responsible for braking to avoid that accident, right? So the vehicle's going to be better capable of handling that situation because it's right there. It instantly sees it. It has the low latency reaction time to avoid the accident. So that's why we're doing the partitioning this way. And, since this is a big systems of systems problem, we had to do a sort of team of teams approach. And this is the set of teams that I've pulled together for Depot Autonomy. So we have a robotics team, which is doing our software stack. We have a team from Nobilis, which is doing the sort of central orchestration. We have another professor here and students doing precise localization. We're working with a startup and with Tech Lab to create an open source robotics test platform. We're getting sensors donated from some of our member companies. Dearborn's helping us with our communication networks. Working with a team in this sort of combined engineering and Ross School to look at investment dynamics of how we would get companies to invest in this, as well as specifically creating the business models. And then we have a team to the spring summer. We have 8 systems engineers working on this because the systems engineering challenge. And then since everybody's going to need to work together, we need an SAE standard, what that means. So we're working together with forward on that through the CAN consortium. So we're starting everything virtually. So this is our virtual depot. It's always better to start your problems in the virtual world, because when you make mistakes, you're just sort of rearranging pixels to fix them, or refactoring your code. It's much easier to do this kind of work in the digital world first. But what we need to do is develop precise perception and motion planning software stack that's informed by the infrastructure sensing. We need to do planning that guarantees safe behavior. We need to be able to generate high fidelity training data. So the digital twin needs to be realistic enough that it can be used to train AI models. And then finally, once we've got it working in simulation, we need to transfer it to the real world. And we don't want that to be a complete tear up, right? We want that to be a fairly seamless transition. So this is our real world prototype. And here's the UMTRI building. You all probably parked somewhere out here, came in through the main lobby, and right now we are right here in the UMTRI building. Out in the parking lot, there's a big tent. It's this tent right here. And that's where we're building, inside this tent is where we're building our physical prototype of depot autonomy. And so this is what it looks like inside the tent right now. We're in the build phase. So we've built this truss structure to sort of simulate the kind of interior infrastructure in a warehouse. And we're in the process of procuring sensors to put onto the truss and procuring compute to put into the depot space. But this will be the place where we'll do all of our demonstration work. And the target we have is to do a large demo of this in August to try and pitch sponsors for continued funding. So then let's dive quickly into maybe some of the more technical work on the approaches. So this is work the robotics team has been doing. They first started out looking at how to make an autonomy stack. And if you look at the different types of autonomy stack, back in the day when we started, 15, 20 years ago, autonomy stacks were completely modular. So it'd be like 20 different modules all doing the job of autonomy. Now, within the last 2 years, you see everybody's doing these complete single end-to-end stacks. The advantage of the many module approach is that when you got an error, you could trace it back to one module, and then you only had to fix that one module. But everybody's moving to these end-to-end stacks because they do the job better than the modular approach does. So it turns out when you take all these modules and start to one big network, one big end-to-end network, that's the job. When things go wrong, you have no idea where in that entire network the error is. So you got to retrain the whole thing. So that's there's a lot less visibility or explainability in these end-to-end networks than there was in the modular approach. So our robotics team chose to split the difference and go with a 2-module approach. Perception module, basically module 1 there, and a planning and control module. And so we'll talk about those. So the first one is this dense reconstruction module for reconstructing the world. The second module is the safe planning module of how do you get from here to your destination waypoint without hitting stuff. So let's talk about module 1 first. So the idea is your input is a sequence of measurements. So we have cameras in the infrastructure and we trigger them all simultaneously and they all take individual pictures of the scene simultaneously, right? So in this case, we have 4 cameras taking in 4 different locations, taking 4 pictures of the scene. What we can then do using 3D Gaussian splatting is we can recombine those pictures into a world model. And so 3D Gaussian splatting is the latest state-of-the-art way to do this kind of work of going from these individual camera pictures of the scene into a cohesive world model that you can then move around in, right? Because once we have this world model, we know where all the occupied space is and where all the free space is, and we can send that to our planner, get to whatever waypoint we want to get to. And that there was the static scene. What we need to do is we need to actually add all the dynamic elements into that scene, right? Because we're going to have vehicles moving around. We're going to have people walking through the scene. So when somebody walks through the scene and the cameras see them, the camera needs to instantly add them into our world model, right? And so the question is, how do we do that? And so the first thing we do is, this person walks into the scene, say, and we can see them. And what we can do, since we've seen camera angles of this person, walking through the scene, we can fit a 3D model to them, a Gaussian splatted model. So we basically make a Gaussian splat of their 3D image. And then what we do is we need to animate them moving through the scene. One way we could do that is we could keep re-Gaussian splatting them every time they move. But that's computationally very intense, right? So we want a more efficient way to do that. So the more efficient way is to think of things like my forearm is a rigid body, right? My upper arm is a rigid body. There's a joint in between, right? So when you walk into the scene, let's just splat the forearm, splat the upper arm, and attach those to a skeletal model that has these rigid bodies that are attached by joints. And so let's take the video of the person walking through the scene. Let's use an optimizer to fit a skeletal model to them. And then let's add that to the 3D model. So it's basically, think of this one here as, a 3D Gaussian splatted exterior fitted over a skeletal model. Right? Think of it that way. And then what we can do is we can insert that in the scene. So if this was a person walking through our tent out there in the parking lot, the cameras would be seeing them, and then the cameras could use optimizers to fit the skeleton to whatever pose they see in the camera pictures, and we can then colorize it with the Gaussian splat model to make it look like the actual person. So this is how we take our static digital twin and add dynamic elements to it and do it in real time. And that's what we think is one of the real research, unique things about this research is a lot of this Gaussian splatting work has been focused either on static scenes or on dynamic scenes that you fit offline and then render later. What we're doing is real time in a Gaussian splatted. So that's some pretty cool work that the robotics team is doing. And then here's the motion planning part. So, typical motion planning, you have your current location, you know where your obstacles are, you have a goal position, you plan a path, and usually people, to save compute, sort of discretize the path and then just check, at these 3 locations that you're not intersecting with the human. But, obviously, depending on your step size, you're missing some spots in between. And so the robotics team was working on using this probabilistic world model that we get from the 3D Gaussian splatting and some sort of known pre-computed trajectories that we know, like in this case, a forklift could take to sort of create a continuous model for intersections between obstacles in the path. So that's the motion planning work that we're doing. And then here's a quick video of a forklift. We got this little box moving, like think of it as a mobile robot, but you see the forklift does this sort of carve out in its path just to make sure it doesn't get too close. So that's the robot planning portion of it. And here's my last slide. I think I left 8 minutes here, so we will have a little bit of time for questions. But our high-level timeline is we're building the test site. It's out in the parking lot. We're targeting having all of our algos complete by early summer so that we can start simulating them outdoors. We're doing all that work virtually right now, like I said, late summer, like August timeframe. Demo for government, industry, academia, so that we can pitch for funding to continue the work.